All right, so we're getting down to the last couple types of factoring in this unit on factoring unit 9. So the last two types of factoring are really just recognizing special patterns. You could use some of the skills that we've learned already this unit to factor these types of things, but if you recognize, for example, unit 9.D5 is the difference of squares, or the difference of two perfect squares. If you recognize that the polynomial that you start with is a difference of two perfect squares, it makes factoring it so much easier because it's just this pattern that develops, which is pretty easy once you see it here in just a few minutes. Tomorrow, then, our next lesson is day 6, and that's going to be another special factoring called the perfect square trinomial. So we'll get to that next lesson, next video, but just wanted to give you a heads up that these are the two different types of special factoring patterns. All right, so the difference of two squares, or if I just call it the difference of squares for short, I'm referring to the same thing. The key there is just understanding what do I mean by the word difference and squares. So when I talk about difference in math, we're talking about subtraction. Okay, so the difference literally means that we are subtracting one thing from another. Now, what are we subtracting? It's got to be two squares, like two perfect squares. Okay, so the difference of two squares is literally just that, word for word. Some examples down below. We have x squared minus 64. That is a difference of two squares. The first thing I notice is there's a difference because it's subtraction. And same thing with the other example. I have subtraction there also. And then for my perfect squares, I just want to make sure that x squared is the result of something times itself. Remember, that's what it means to be a perfect square. It's the result of multiplying something times itself. So we could think of x squared as being x times x, and we know that 64 is 8 times 8. So there we have a difference of two squares. Now I haven't factored anything yet, but I'm just recognizing that that is a difference of two squares. In my next example, I had 4x squared minus 25. And the 4x squared is if I were to take, well, 2 times 2 is 4, and x times x is x squared. So 2x times 2x is 4x squared. In other words, 2x squared is 4x squared. And then the 25, of course, is just 5 times 5, or 5 squared. Okay, so we have a difference of two squares, two perfect squares. So let's just recognize if we have a difference of two squares in our examples here. So which of these polynomials is a difference of two squares or not? So in the first example, we have x squared minus 81. Well, I know x times x is x squared, and I notice that 9 times 9 is 81, and it's also a difference because it's subtraction. So we are going to go ahead and move that one over here. It is a difference of two squares. Our next example, x squared plus 16. Now this one actually is not a difference of two squares. Can you tell why? It has two perfect squares in it. X times x is x squared, and 4 times 4 is 16. The problem is it's not a difference example. It's a plus sign. That would be like a sum of two squares, and that is not a special factoring pattern. All right, next we have 9x squared minus 100. Think about that one. Well, it is a difference, so no trick there. There's subtraction in it. But are those two perfect squares? You know, can you think of something times itself that equals 9x squared? Well, 3x times 3x is 9x squared. And 10 times 10, of course, is 100. So that is a difference of two squares. 25x squared minus 200. Well, I know that 5 times 5 is 25, so I guess 5x times 5x is 25x squared. It's a subtraction problem. What about 200? 100 and 100? No, wait, 100 times 100 is way bigger than that. That's like 10,000. 14 times 14 is 196. That's as close as we can get. 200 actually is not a perfect square. So that's not a difference of squares. So I would not be able to factor that using this pattern we learned today. X squared minus 49. Well, yes, it's a subtraction problem, so it is a difference, but are they perfect squares? X squared is x times x. 49 is 7 times 7. So that is a difference of two squares. 4x squared minus 1. Now let's see. So it's a subtraction problem. We're good there. I know 1 times 1 is 1, so that's a perfect square. What about 4x squared? 2 times 2 is 4, so 2x times 2x is 2x squared. Yeah, that one works also. That's a difference of 2 squares. And here we go. I think this is our last one. 2x squared minus 36. I see the subtraction. I know that 6 times 6 is 36, so that's a perfect square. But what about 2x squared? 2x times 2x would be 4x squared, so that doesn't work. X times x is just x squared, so that doesn't work. The 2x squared is not a perfect square. That one's just not quite going to work out. Okay, so the only time that we can factor what we're doing today, the thing that you're going to learn here in just a moment, is when you have a difference of 2 squares. So we have to recognize that at the very first step. So here's our pattern. This is how we factor a difference of 2 squares, and I'll show you why that works here using an area model. So a squared minus b squared, if you can figure out what a equals, in other words, what squared equaled that first term, we basically just take that a, put it at the beginning of each binomial. Then we have the b, or the second part squared. Okay, in other words, the square root of the second part is what's going to go at the end of each binomial. And then you'll notice that we have one that has addition and one that has subtraction. So they're not the exact same, but they're very similar. The only difference in our binomial factors there in the parentheses is that one has addition and one has subtraction. So if I use my area model to prove that, or to show how I get a squared minus b squared, I started by setting up the a plus b on the side and a minus b on the top. So there's my area model showing how to multiply my two factors together. So a times a is a squared. A times negative b is negative ab. In the bottom row, a times b is positive ab. And in the last box, a positive times a negative is negative. B times b is b squared. And when I take all these and write it out using my area model for total area, I get a squared minus ab plus ab minus b squared. Well, I notice I have like terms because they both contain the same variable parts, and I have my invisible ones as my coefficients. And when I add those together, I actually get 0. They cancel out because they are exact opposites. So I literally end up with a squared minus b squared. It is a difference of 2 perfect squares. So working backwards, if I have a difference of 2 perfect squares, that means that these two, these two like terms are going to always add up to 0 and cancel each other out. And that's going to happen if we have this exact factoring pattern of a plus b times a minus b. So let's look at our example here. X squared minus 81. First of all, is that a difference of 2 squares? Difference of perfect squares? Well, I recognize that x times x is x squared. I also recognize that 9 times 9 is 81. And yes, it is a subtraction problem. So if I follow my pattern, I know that 1 has to be plus, 1 has to be minus. I do x times x to give me x squared. And I add 9 times 9 to give me 81. Technically, it's 9 times negative 9, and that's how we got the negative 81. Okay, in number 2, we had 9x squared minus 100. Let's see, is that a perfect square? I know that 3 times 3 is 9, so 3x times 3x is 9x squared. I also know that 10 times 10 is 100. So for my factoring, I have a plus and a minus. I do 3x times 3x to get the 9x squared. I add 10 times the negative 10 to get negative 100. So there's my special factoring. For number 3, 4x squared minus 1. Well, let's see. 2 times 2 is 4. So that must be 2x times 2x to get 4x squared. And 1 times 1 is 1. So my special factoring is going to begin with 2x at the beginning of each one. One's positive, one's negative, and then I just put my ones in place. And last but not least, number 4, let's see, 25x squared should be 5x times 5x. 144 is 12 times 12. It's a subtraction. So we have a difference of squares, so we can go straight to our little pattern. One's plus, one's minus. 5x at the beginning of each one, and I put 12 at the end of each one. You can always double check your work by using the area model to check and see if it actually equals what you started with. And if you're ever wondering, it certainly is a good thing to do. It's just to double check to be safe.